Bore da everyone! So today's lesson is going to be on waves. You're going to need the assignment out next to you ready to fill in questions as we go through the lesson. So for the do now activity, I want you to look at the image and describe what it is, and then think about any other types of wave. So pause the video now and write any comments you have on the assignment. Okay, so the aim of today's lesson is to understand the types of wave, to be able to identify the main parts of the electromagnetic spectrum, to understand the relationship between speed, frequency and wavelength of electromagnetic spectrum waves. So we're going to start with describing waves. There are two types of waves, transverse and longitudinal waves. So transverse waves describes waves in which the direction of motion of the wave is at a right angle to the direction of vibration. For example, like water waves. Longitudinal waves describe waves in which the direction of motion is in the same direction as the direction of the vibration of the wave, like sound waves. Transverse waves travel as a series of peaks and troughs. Longitudinal waves travel as compressions and refractions. Okay, so in the diagram you can see two different types of wave using the demonstration of a slinky. From the descriptions that we've just talked about, I want you to have a think about which one you think is the transverse wave and the longitudinal wave. Okay, so read over these descriptions one more time and then think about what wave is which in the diagram. Okay, so the top one is a longitudinal wave. The direction of vibrations and the direction of the wave is in the same direction. But as you can see in a transverse wave, the direction of the wave is perpendicular or at a right angle to the direction of vibrations, or the direction of wave motion. Okay, so this video is going to show this demonstration.
Hi guys, today I just want to show you a demonstration of transverse and longitudinal waves using a slinky. Now, transverse waves, the direction of energy is going to be going forwards, and that's the same with longitudinal waves as well. The energy is going to go this way. But with a transverse wave, the medium, so in our case the slinky, which is what the wave is going to travel through, is going to be moving perpendicular to the direction of energy transfer. So let me give this a go. So you can see the pulses or the waves are moving from the left to the right. So the energy is moving from the left to the right, but the actual slinky itself is moving perpendicular to the direction. Now another kind of wave is a longitudinal wave. Now with a longitudinal wave, the medium, again which is the slinky, moves in the same direction as the energy transfer. So the energy is moving in this direction, our wave is going to be, or the medium, the slinky, is also going to be moving in this direction. So this is a longitudinal wave, like sound is also a longitudinal wave. So in this case, you can see that there's a part where the wave gets compressed and a part where the wave gets rarefied, and that these pulses move along in the same direction that the energy is flowing. So that's a longitudinal wave, like that. That's a transverse wave. Okay, bye for now.
Okay. So we now need to look at how we can describe waves. Waves are described in terms of wavelength, frequency, speed, and amplitude. Wavelength is the distance that a wave takes to repeat itself. It is measured from the crest to crest of the wave. Wavelength is measured in meters. And as you can see here, this is the symbol for wavelength. Frequency is the number of waves that pass a point in 1 second, and it is measured in hertz. 1 hertz being equal to 1 wave per second. Again, This is the symbol for frequency. Speed is the distance that a wave travels in 1 second and is measured in meters per second. As you can see here, this is the symbol for speed. Finally, amplitude is the measure of energy carried by the wave. It is measured from the undisturbed or normal position to the top crest or bottom of a trough. Loud sounds have larger amplitudes. Okay, so we can see what we've just described in this diagram. Here we have the amplitude. From crest to crest we have the wavelength. This is the undisturbed normal, so as you can see where the amplitude is measured is when it changes. Okay, so now we need to pause the video and have a go at the review activity. So you first need to write the type of wave next to each statement. A. The direction of motion of the wave is at a right angle to the direction of vibration. Is this transverse or longitudinal? B. The direction of motion is in the same direction as the direction of vibration of the wave. Is this transverse or longitudinal? C. Water wave, and D. Sound wave. Which wave are they? What is meant by the wavelength, frequency, and speed? So pause the video now and have a go at those activities. Okay, so we'll start with the first one. The direction of motion of the wave is at right angles to the direction of the vibration. This would be a transverse wave. I've just written TRL for each type of wave. The direction of motion is in the same direction as the direction of vibration of the wave. This will be longitudinal waves. Water waves are an example of transverse waves, and sound waves are an example of longitudinal waves. So what is meant by wavelength, frequency, and speed? Wavelength, which I've written in red, is the distance that a wave takes to repeat itself, and this is measured in meters. The frequency, which I've written in orange, is the number of waves that pass a point in 1 second, and this is measured in hertz. And finally, speed, which is in blue, is the distance that a wave has travelled in 1 second, and is measured in meters per second. So we're now going to watch a quick video that summarises the different types of wave.
Waves. One of the first things we need to know about waves is there are two different types of wave. One shown here by waves in the sea, and the other one shown by sound waves. So how are they different? Well, first let's look at the sea waves. If we look at them represented with this slinky, we see that the vibrations are at 90 degrees or perpendicular to the direction of travel of the wave. These are called transverse waves, and examples of them are waves in water, waves on a string, or light waves. Now let's look at the sound waves again. Again, we see them represented by the slinky, but this time the direction of vibration is parallel to the direction of travel. These are called longitudinal waves, and the only example you really need to remember is sound. One really important thing to remember about waves is they only transfer energy from place to place, not any matter. And we can see that here by looking at a lovely rubber duck sat in a bath. As a wave goes through, the duck bobs up and down, but once the wave's gone, he's back to his original position. The wave has carried energy through, but it did not carry the duck with it. Finally, we need to know some key features of waves. First off, wavelength. A wavelength is the length of a full cycle of a wave, from one point to the next same point. It's easiest to think of as the distance from crest to crest or from trough to trough. And we measure it in meters, and it's given the symbol lambda, a nice Greek symbol. The amplitude is like the size of a wave. But we need to remember that it's measured from the equilibrium position, or the central line, to the crest, not from the crest to the trough. Finally, frequency, which is the number of complete waves to pass a point every second. And it's given the unit of hertz. So an example of this would be if 10 waves pass in 2 seconds, the frequency would be 5 hertz. Using these things, we can actually now calculate the speed of a wave using the equation speed equals frequency times wavelength, or to give it in symbol form, V equals F lambda. So there's a lot to learn here, but once you've learned these core concepts.
Okay, so bearing in mind what we've just been through, I want you to pause the video and have a go at labelling the diagram. So you need to label the wavelength, the amplitude, peak or crest, trough and frequency. Don't worry about the period. Okay, so we're now going to look at the calculation of wave speed. So we can calculate wave speed using the following equation. Wave speed equals frequency times wavelength, or I've written the simple equation below. Waves travel at all different speeds. All electromagnetic waves travel at the speed of light, which is equal to 3 times 10 to the 8 meters per second. So it's very, very, very fast. Water waves travel at about 4 meters per second, so a lot slower. The next part of the lesson is looking at the electromagnetic spectrum. These are a family of transverse waves that all travel at the same speed, the speed of light. So as we can see here, this is the speed of light, which I've already mentioned. These waves are called radiation. So here we have a diagram of the electromagnetic spectrum, and it's written in terms of decreasing wavelength and increasing frequency and high energy. So as we can see here, where our radio waves are, this has the longest wavelength, but also the lowest frequency and lowest energy. We then have microwaves, followed by infrared, visible light, ultraviolet, X-rays and gamma rays. At the gamma rays, we can see that these have the shortest wavelength, but the highest frequency and the highest energy. So we can see the frequency changing by the line, which I've circled here. So going across, you can see at the beginning, with low frequency and long wavelengths, the waves are far apart. However, towards the high frequency and short wavelengths, they're a lot closer together. So a lot more waves are happening per second. Okay, so we're now going to watch a short video summarising the electromagnetic waves.
In today's video, we're looking at the electromagnetic spectrum, which is this entire range of electromagnetic waves, and will cover both where they come from and what happens when they're absorbed. The first thing to know is that electromagnetic, or EM waves, are all transverse waves, which means that they oscillate perpendicular to the direction of energy transfer, so up and down. And when they're in a vacuum, they'll all travel at exactly the same speed of 3 times 10 to the 8 meters per second. When they're in different mediums, though, they'll travel at different speeds, and this can lead to refraction, which is where the wave changes direction. As you can see in our table, we split electromagnetic waves into 7 basic types. but they're actually all part of one continuous spectrum. What differentiates them is their wavelength and their frequency, which are inversely related, which means that if one goes up, the other one goes down. So if you read the table from left to right, the frequency increases while the wavelength decreases. So radio waves have the biggest wavelength but the smallest frequency, and gamma rays have the smallest wavelength but the biggest frequency. And to give you a rough idea of the wavelengths, they vary from multiple kilometers for radio waves to less than 1,000th of a nanometer for gamma rays. As human beings, though, our eyes are only able to detect a tiny part of the spectrum, which we call visible light. And the different wavelengths within this region are what give us all of the different colors that we can see. Now, one of these slightly annoying things about this topic is that you need to memorize the order of all the different waves in the spectrum. Personally, I think the best way to do this is to start in the middle with visible light and work your way outwards. If you don't know the colors of the rainbow already, you can remember them as Roy, G, Biv, or red, orange, yellow, green, blue, indigo, and violet. After violet comes ultraviolet, which makes sense, and before red is infrared. To help you remember that X-rays and gamma rays are over on the right, remember that all of these types, so ultraviolet, X-ray, and gamma, can all be ionizing and cause damage to our cells, so they're grouped together. Then all we have left are microwaves and radio waves, which are both used in communication and go on the far left. The last thing we need to cover is where electromagnetic waves come from. The short answer is that they come from everywhere. Don't worry about remembering the exact details, but to give you some idea, radioactive decay can cause gamma rays to be emitted, while visible light, ultraviolet, and X-rays can all be emitted when electrons drop down energy levels. And when the bonds that hold molecules together vibrate, it can generate infrared radiation. So really, radiation's emitted from all over the place by loads of different things. Once they've been emitted, all of these waves can then travel across the universe through empty space. And when they come into contact with something, they can be either reflected, absorbed, or transmitted. Or sometimes a combination of these three might happen.
Okay, so we're now going to look into the uses of electromagnetic spectrum. So different parts of the spectrum have different wavelengths, frequencies, and energies. The higher the frequency of a wave, the higher the energy will be. All three, wavelength, frequency, and energy, determine the properties and the use of the waves. So we're going to start at the longest wavelength. So radio waves have the longest wavelength, however they have a low frequency and low energy. These are used for communication over long distances, for example, transmitting TV and radio programs. Microwaves is the second longest wavelength. These also have a low frequency and low energy. They're used for heating and communicating, for example, microwaves or mobile phone signals. Infrared radiation has a relatively long wavelength, a relatively low frequency, and a relatively low energy. It is used for heating and communication. For example, TV remote controls and optic fibers. Visible light is at the middle of the spectrum, and it's used for seeing. So as you can see, we see all these different colours: red, orange, yellow, green, indigo, and violet. So ultraviolet light comes after visible light and has a relatively short wavelength and then a relatively high frequency and energy. It can ionize skin cells, causing sunburn, but it can be used to detect forged banknotes. So ultraviolet light comes from the sun. Okay, the next one is X-rays, and this has the second shortest wavelength with a high frequency and high energy, and it is also ionizing. It can be used for medical imaging. Finally, we have gamma rays, and this is the shortest wavelength, and it has a high frequency and high energy. It can ionize and kill/damage cancer cells, and can also be used to make images of the body. Okay, so as we saw in the video, short wavelengths such as gamma rays, X-rays, and ultraviolet are all ionizing radiations. This means that they can interact with atoms and damage cells due to their high energies. Okay, so in your exams, you'll need to remember the order of the spectrum. So the order goes from long wavelength to short. And we can use different things to remember this. So as you can see here, I've used rainbows might interest very unique, extraordinary giraffes. So I can know that the first one, rainbows, is radio waves, might, microwaves, interest, infrared radiation, very, visible light, unique, ultraviolet, extraordinary, X-rays, and giraffes, gamma rays. Okay, so I want you to have a go at making a mnemonic to remember the order. What I mean by this is make one of these. So write down R, M, I, V, U, X, and G to think about a way that you can remember the order of the electromagnetic spectrum. So pause the video and have a go at this now on your assignment. Okay, now that you've done that, I want you to complete the review. So you need to use this mnemonic that you just made to write down the electromagnetic spectrum in order. You need to label the longest and shortest wavelength and the highest and lowest frequencies and energies. In question 2, you need to describe what speed does all the spectrum waves move at. So remember, this is the speed of light, and we mentioned this earlier. The next, we need to write down the equation for wave speed. Also, we mentioned this earlier. You then need to complete this table in the assignment of the uses for electromagnetic spectrum waves. You can use the video to help you with these. I'm not going to go through the answers in this video, but I will be looking at your assignments to check what you have put. Okay, so for question 1, this is what I mean. So write down what you come up with to help you remember, and then write down radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, and gamma rays next to the correct letter. And then you need to label which is the longest wavelength, low energy and low frequency, and then down the bottom, the shortest wavelength, the high energy and high frequency. Okay, so well done for concentrating the lesson, and make sure you submit your assignment. If you have any questions, you can use the comment box in the general page on your Teams account.